Okay, that looks like it's working. Okay. Yeah, so before I get started, I'll keep waiting for people to trickle in. Sorry for starting the meeting a little bit late. Does anybody have any questions right now regarding literally anything?
I have a question, Chuck.
Yeah.
While we wait, I didn't prepare to ask this, but I was working on a separate project and I'm trying to, I ran a regression and then I had predictive values and I was trying to add that as a column and I was trying to add it as a data frame, but I was getting a different number of rows. And the really weird thing is that when I try to get the number of rows for that data frame of just the predictive values, if I just looked at it in the viewer or if I got like a tail, it would be the right number.
Yeah.
But if I just put it in n row, it would be a different number.
That's interesting. I'd have to see the exact case. There's a couple things that can be the case is that, well, so
and there were no NAs.
Yes, that's what normally would be something like there's NAs. I would have to see the exact case. So you're essentially getting different row numbers from the same object in different cases?
Yeah.
Okay, yeah, I'd have to see the exact case. If you produce a reproducible example or something, or send me maybe a couple like screenshots, something like that, I can try and take a peek, but that's not something I can't think of immediately anything that might be without seeing the functions being run.
Yeah, that makes sense. I'll send you some screenshots later in Slack.
Okay, sounds good.
Thank you.
Okay, still people creeping in. I'll start in like a minute or so. Okie dokie, well, I'll just start yammering. Okay, so last week, of course, we had a grueling unit on writing loops. And as I kind of promised last week, I was going to then immediately talk about how to not have to write those loops. And so a lot of what today's lecture is how we can perform the same sort of tasks faster and easier without writing loops. So it's really nice to know how to write loops for those problems you can only solve with them. The thing is most problems can be solved without a loop. And we're going to kind of talk about how to do that. And part of that is writing your own functions. So if you were in lab, you saw me write a function or two just for some quick stuff. I wrote my own operators to do the opposite of %in and things like that. It's a function like anything else. So yeah, today's going to be how not to loop and how to write functions. And how to not loop requires you to write functions. So these things go together. Okay. A quick aside, though, before we start on that, is sort of some general advice for doing any sort of tasks with data. And technically, this is really just general programming advice, okay? So before you can write effective code to perform any task, you need to know exactly what you want that code to produce. You don't want to start writing code to do something if you have no idea what it is you want to generate. Ah, the cat has returned. If she doesn't settle down, you're all going to get to see a cat. Okay. Anyway, so the idea is that you need to ask yourself, do you want a single value? Do you want a vector? Do you want a list as your output of whatever you're running? Do you want one observation per person year, per year in your data or something like that, right? These are sort of the questions you ask when you'd be grouping or summarizing your data and generating things like that, right? Okay. So most programming problems you'll encounter can be reduced to having some unclear idea of your end goal. If you don't know where you're going with what you're doing, you're not going to get there, right? You don't know what you want and you're just kind of stabbing around in the dark, hoping you're going to end up with something. It's not a very effective way to get the job done. Another problem you may have is you know exactly what you want in the end, but you actually don't know what you have to begin with. And so this is something that I tried to drill in a little bit in this previous homework, was you need to figure out the beginning state of the data you're working with. If you don't know what your columns are or the format of those columns, weird stuff that's in them, you're going to end up with unexpected results, okay? So the first step in sort of any general project is figuring out exactly what you've got, and exactly what you want is the second step, right? So if you know what you've got, right, that is the structure of your existing data, and you know what you want, those intermediate steps are usually obvious. And it might be obvious in an abstract way, not necessarily the exact functions you need to run, but you probably mechanically have an idea of how to do it, okay? So when in doubt, what I do anyway is I will sketch my beginning state. I will draw it up on a whiteboard or something like that. I'll just draw out the first few columns and rows of the data. And then I will draw some representation of the end state. And then I will consider, like, mechanically what operation would translate the former into the latter. That is, if I had a piece of paper like those data and I cut up all the cells, how could I rearrange them puzzle-like into the second thing? If I can figure out the paths the cells have to take to go somewhere else, I can figure out how to write code to do that if I know the functions that will do those operations, right? So if you can figure out how to translate the beginning state to the end state, you'll be able to figure out a way to do it, okay? If it seems complex to do it, try and figure out something intermediate between those things, and you'll break it into steps. Most sort of big programming problems you encounter will just really be a set, the answer to them anyway, will be a set of relatively simple steps. Many, many, many steps. This is already what we do with dplyr, right? We want to go with some data set, we want to end up with something else. We just run one function that does one thing. It goes a little bit closer to what we want, a little bit closer, a little bit closer, a little bit closer, step by step by step by step, right? Each one of those steps you can think of as a discrete action you're taking to take your original data and go to something later, right? Now, in like professional software development, often each of these little discrete steps would be its own script file or something like that, its own operation done separately. This is something called a software development or a software pipeline, and I'm going to talk about pipelines all the way in week 10. Okay. So anyway, on to the main topics. Vectorization. So you might remember from last week, we tried to find the mean for each variable in the Swiss data set using a loop, right? You had to write a bunch of code to do it. It was nice because it would work for a data frame of any size, right? But as I said later in that lecture, the best solution would not be to write a loop for that. It would be to use a function like call means without thinking about pre-allocation, without thinking about what to iterate over or anything like that. You can just say, give me the column means of Swiss, and it will give you the column means of Swiss without running a loop or anything like that. It will also do it a lot faster. This column means function runs much more quickly than your loop did because it's more efficiently written code. Usually because under the hood, it's written in another language or something. Call means may actually be written in R. I still guarantee it's faster than any loop you're going to put together, okay? So loops are really powerful, and basically anything you would ever want your computer to do, you could make a loop to do it. It would almost always be the wrong decision, but you could sure as hell make your computer do it with a loop, okay? Vectorization in R is a way to avoid writing loops or any other explicit iteration type operation and still perform a repetitive task, okay? So loops are slow. They require writing tons of code. Vectorized commands are neither of these things. They tend to be concise and fast. So whenever possible, you should use vectorized commands, things like call means I showed earlier, or basically everything in dplyr is vectorized. You'll notice that when we want to create a column in dplyr with some syntax, when you create, like use a formula on the left side of mutate, right? It does that formula and applies it to every cell in that like table and generates a whole vector of responses, right? You don't have to go in dplyr and do it row by row or cell by cell. It does an entire column or an entire set of columns or something like that. This is something that's vectorized, and we haven't even had to think about it. We're just used to the idea now that, oh, if I say take this column times this column, it's going to do it for every single value in there. That is actually something not completely unique, but is sort of unique to R in that it does these like column-wise vectorized operations. There are many programming languages that you have to explicitly work on every single one of those elements one by one, and thus you have to use loops. The whole point of the structure of R is never having to do that sort of thing, right? Okay. The thing is, though, is sometimes no function exists to do the thing you need to do, right? You have some sort of operation to do on columns or rows of your data, and you don't know how to do it. So you might be tempted to write a loop to do it. You're like, well, I can figure out how to do it cell by cell, so I'll just do it with a loop. This does make sense if you have some fast one-time operation and your data set is relatively small. If you're working with 10,000, 20,000 rows of data, you're only going to run this thing once, and it's a relatively basic operation. Your loop might be just fine, okay? It's fine to use loops for simple tasks if it makes sense. The issue is if you have a large data set, like a legitimately big data set, you start getting deep into the hundreds of thousands of rows, the millions of rows or something, no matter what you're doing, your loop is probably going to start to get a little bit slow. And if you're going to do this task repeatedly, every time you write that loop in your code, it's going to eat up like an entire page in your script, right? Loops are really big. You're going to rapidly start to clog up your script file. I would recommend that if you're going to be working on large data or you're going to do some operation multiple times, instead of writing loops for every one of these, you should write functions to perform these tasks. Ideally vectorized functions, but if not, there's a better way to iterate than loops I'm going to get into also. Okay. So you need to be able to write your own functions. The real power in R as sort of a functional programming language is in writing functions to perform tasks for you. Most of the operations you're going to do, somebody has a function for it, but once you've harnessed the ability to write functions for your tasks, your code will get more concise, faster, easier to read and stuff. So this is really important and powerful. So examples of existing functions that use all the time are everything you've ever used with a parenthesis in it in R, and plus all of your operators, right? Anything that isn't like a data frame or a vector or a matrix is a function in R. So common examples we've used are things like mean, and I will get to that question in a second here. The mean, it takes as an input some vector, it outputs a single number, the mean of that vector. Another thing would be filter and dplyr. It takes as an input first a data frame and second a series of logical conditions. Its output is a data frame where rows are removed if they don't meet those logical conditions. Read CSV in reader is a function. It takes as an input just a file path on your computer and maybe some optional variable names or types or things like, is there a header or not? And its output is a data frame containing info read in from that file. Okay, so this question here was, do you keep a master R markdown with a list of your most commonly used custom functions? I do not. I don't actually have documented or shared anywhere my most commonly used custom functions. Occasionally I introduce them in class or in lab, but I don't document them because most of them are custom to very specific situations, and so they wouldn't probably be useful to people, aside from some of the ones I show in lab, like %NotIn is a function that should be in base R, but isn't. It's incredibly useful. I will show one of my most commonly used custom functions at the end of this lecture, and I can pretty much guarantee none of you will ever want to use it, but it's a cool demonstration of being able to do lots of stuff in a function. I'm going to show you the function that generates the lectures for this class. It does a lot of things at once, and it kind of shows you how the functional stuff saves you a lot of coding and time. Okay, so why would you want to write your own functions, right? So most things you want to do in R, a function probably exists to do it. But sometimes you have to use multiple functions, say, to perform a task. You can collapse them all down into one function call, things like that. So functions can encapsulate repeated actions such as these. Maybe you want to, given a vector, compute some special summary statistics. Maybe given a vector, you want to give it a definition of invalid values and replace them with NAs. Maybe you want to generate templates for your favorite ggplot to use in reports, so you don't have to generate that huge block of ggplot code every time you make a plot, right? Advanced functions, that are things I'm not going to cover in this class, would be writing functions to enable parallel processing to take advantage of all the cores on your computer. So most computer, basically every computer any of you will ever have, has multiple processor cores in its CPU. Languages like Python and R by default only use one of them, meaning they're not using very much of your computer's capabilities. If you really want to speed stuff up, using multiple cores will make things a lot faster. Another thing is a lot of packages we use, the functions you call on them actually generate other functions. So this is called metaprogramming. You have a function that makes functions for you. That's actually what the dplyr or dplyr's pipe does. You pipe together all your functions, and what it's actually doing is taking all the commands you give it, stitching them together into one big function and running that function behind the scenes. That sounds like magic, and it kind of is, but it is a more advanced topic for function generation. And another thing, which is sort of hinted at here by Alexander's question here, is you might make custom packages of your own that contain the functions you commonly use. I used to have my own package on my computer that contained my custom functions, but nowadays I usually just define the few that I'd use in any script at the top. So the question he had here was, is best practice to just put those custom functions in at the top right under our loaded libraries? That is what I usually do. If I generate a custom function, I'm going to use it in my script. If it's a short function, I put it right up top of the libraries. If it's something that is longer and I'm going to use it next to some data I'm showing and it's a script I'm going to show to other people, I'll define the function down right before it gets used because the documentation for it will be in the function rather than where the function is used. So it kind of depends if I want people to see it or not. Okay, so a lot of things you can do. Well, these first three things, computing special summary stats, replacing things with NAs, and doing templates are the examples we're going to use in today's lecture for writing our own functions. Okay, so here's a simple function. I'm going to show you this example of a simple function, and then I'm going to talk about in the abstract what this is going on here, so it's okay if you don't understand everything going on here. So this simple function here is a function that takes a vector as an input and it outputs a named vector of the first and last elements, okay? So the idea here is I'm going to create a function named first and last. I'm going to assign to first and last a function. So in R, the function that writes functions is called function, okay? It's easy to remember. If you want to make a function, you use the function, which means we're going to say function a lot. So I'm saying here, I'm going to create a function which takes the argument x, and then everything in here is stuff that runs when the function runs. This says, create something named first, which is equal to the first element of x, create something named last, which is equal to the last element of x. So x subset to the length of x. Length of x is however many elements there are. So this subsets to the last element of x. And then it will return, that is, it will, when this function is done running, give us whatever's in here. It will return a vector where the first thing is named first and the last thing is named last, okay? So if I run this function, I can say, give me the first and last of 4, 3, 1, and 8, and it reports the first is 4 and the last is 8. This is a very simple function, but this is just, you could write your own function if for some reason you consistently need to get the first and last values of vectors. Just works, it does what you want. Okay, but this function has problems, okay? So if I give first and last a vector of length 1, what does it do? If I say, give me the first and last of 7, it's gonna say the first value is 7 and the last value is 7, right? That's because if I go back and look in the body of this thing, it takes x, its input, and subsets it to its first element. Its first element is 7 because it only has one element. But over here, it says the last element is x subset to the length of x. Well, its length is 1, so this thing and this thing do the same thing. So first and last says its first and last is 7. Maybe this is what you intend for this function to do. Maybe it's not. You might want to make it smarter than this if you're not expecting length 1 vectors. What happens if I give it a length 0 vector, right? This is something that I've shown before, is that there are vectors in R which are length 0. If I say numeric 0, it creates a numeric vector with no elements. It's empty, there's nothing in there, but it's still a numeric vector. If I say first and last numeric 0, it just returns an NA. Okay, it doesn't kick an error message or anything. It just happily gives me an NA. There is no first element. There is no last element. It can't find anything. They're missing. It returns an NA. Okay, so we might want it to be a little bit smarter. And the idea here is that our functions we write are only as smart as we make them. Okay, if we want to be able to handle special cases like this, we're going to have to use some of the tools we learned in the last lecture. So what we can do is we can take the code for this function and add in some of those if and else statements we got from last week's lecture. So let's do something like this. Let's make it give us an error message when the vector is too small. That is, when the vector has no length. I'm going to say we're going to make a function called smarter first and last. We're going to assign to it a function, which again takes a single argument x, and then the body of it is now longer. What we're going to say is, if the length of x is 0, this is an integer 0 here, 0L if you remember this from an earlier lecture. If the length of x is 0, I want you to stop running the function and holler at me the input has no length. That's all stop does, is it generates an error message. Some of those error messages you've seen other functions generate are generated using the stop command, okay? Else, in other words, if the length is anything other than 0, do the exact same thing you did before, okay? Now, if I say smarter first and last numeric 0, it will say error in smarter first and last numeric 0, the input has no length. This looks like the other error messages you've probably seen in R, because those error messages were written exactly like this, right? They look for something that they're not expecting, or they check to make sure something is what is expected. And if that is not the case, it stops the function and spits an error. If, however, I give it some other argument that has a length, it works perfectly fine. It continues on just as we did before, okay? So this is how you'd make your functions a little bit smarter if you need them to. Most of the functions that I write and I do in my data analysis have very little error checking built into them because I've already dealt with that earlier in the script. I've gotten rid of my NAs, I've made sure my lengths are correct and everything, so I can give them a function that doesn't need a lot of special case handling. But sometimes you're going to want to write functions that know how to handle all sorts of special situations, or you just want to write functions that kick you warnings on certain things. Like maybe you've got functions that just look down all the different columns in your data and look for weird shit. Right? They look for values that are too high or too low, negatives when they shouldn't be negative, looking for character values and things you expect to be numeric, that kind of thing, right? Okay. So if you type a function name in R without any parentheses or arguments, it will show you the code inside of that function. Okay, if I type smarter first and last, which I just wrote, it will show me all the code that was inside smarter first and last. You can also put your cursor over a function in your syntax and hit F2, it'll do the same thing. So if I come back over here and I pop open RStudio, I'll show you. Okay, so if I open my console and I say something like, let's see what call means looks like. That is the function that actually does call means for us. Okay, it's written in our code. It looks complicated because most of us aren't used to writing code that's used in packages. Most of this is error checking, right? This says this is a function which takes x as an argument. It has two additional options, na.rm equals false and dims equals 1. I don't remember what the dims argument here does. na.rm equals false means I can say na.rm equals true and it will drop nas from those columns. But then inside it does things like, oh, if I give it a data frame, it converts it to a matrix before doing calculations. If it gives me an array, or if it gives me an array with too many dimensions, it says it must be an array of at least 2 dimensions. If it gives me something with wrong dimensions, it says stop, there's invalid dimensions. If all these checks get passed, it goes on and calculates our means, generates them, and spits out a vector with our names of our dimensions and the means of all of them, okay? You could replicate or write your own function to do this if you wanted to. So almost all R functions you use, if you dig deep enough, you can see exactly how they're written. R doesn't keep secrets from you. This is not like the code inside some software like SPSS or something where you got no idea what's going on behind the scenes. In R, once you get better and better with it, sometimes cases will come where you're like, a function is breaking, I have no idea why, crack it open and find out why. That's a much more advanced thing. I wouldn't expect anyone here to be doing that anytime soon, but it's something that like people have been doing this for 3, 4, 5 years. You start to debug things like that to be like, well, this thing shouldn't be breaking. And maybe you find there's an actual bug or error in it. I found a couple major like statistical packages that had edge cases where they break when they shouldn't break. So I just steal the code inside their function, fix it a little bit, and run the statistical routine myself. Open source software is amazing, right? Okay. So to the abstract here, the anatomy of a function, okay? So functions have a name, right? Like any other object in R, the name is just what you are assigning it to so that you can call on it and use it later. You can have what are called anonymous functions in R. An anonymous function is a function you use but doesn't have a name. We're going to see how to do this later. You call on it once and it just sort of disappears. Anonymous functions, okay? Then they have arguments. So inside the actual function call right here, you provide arguments you want your function to have, right? These are the inputs or the parameters, the things the user will pass to that function that change how it works. It's possible to write functions that don't have any arguments at all. You might have a function that you hit a button and it just does something in the background, right? You might have a function, you run it, it takes no arguments, it pings the speaker on your computer, makes it make a beeping sound. I use that for really long scripts when I want to know they're done. I just, at the end of it, it runs a function that pings my computer speaker, okay? So you can give them arguments. You'll notice up in here that I've got like argument 1 and then argument 2 equals default. If you provide argument equals something, if the user does not provide an argument 2, it will just use the default by default. This is how you write a function that, well, you can change this if you want to. If you don't provide it, it just works. Almost every function you commonly use in R has a ton of these defaults. If you go into a help file, like, this is a classic one. Let's go to read.table, which is basically read.csv. Look at all the arguments this function takes, right? It takes all of these as arguments. But you'll notice every single one of these except file has a default set on it already. This means you can do read.table or read.csv providing it only a file name, but you have the option of setting every other one of these arguments in it for special cases. If you think about it, you'll probably realize that most of the functions we use in like dplyr and stuff like that have a ton of these optional arguments we can give to them. We just normally don't give them anything. Somebody had to write those arguments in there, though, and give them a default so that you can provide an argument to it if you want. Okay. The thing is if you assign something to argument 1 or argument 2 by giving it as an argument to that function, even if that thing is assigned to a value inside the function here, it will only exist inside that function, okay? Things that are assigned to arguments only exist in the environment of the function. Once that function is done running, they will not be accessible to you again. This is the opposite of loops. Loops, anything created in a loop just goes into your global environment. Anything created inside a function doesn't get created in your global environment, okay? Unless you manually assign it in a very specific way inside the function, which is hard to do and I don't teach in the class because you shouldn't be doing it. If you want your function to assign something to the global environment, you run the function and assign its output on the outside of the function to something. Okay. So the body of the function here is where you put all of the actual operations you want the function to do. This can be any arbitrary things. It could be hundreds of lines of code, as is the case in some complex statistical routines. It could be a couple lines of code, 1 line of code, something like that. Okay. And then the final thing inside a function is a return statement, okay? The return, anything given as an argument to return will be spit out by the function once it's done running, okay? This could be a vector, list, a data frame, another function. It could also be nothing at all, right? Return specifies what's gonna pop out when it's done running. It can, however, be only one thing. Your function, like any other function in R, can only generate a single object at a time. This is sort of a restriction that R does, which is a good restriction. You don't really want functions to be able to populate your environment with 10,000 new objects or something, right? Return can only take one object. If you do not specify a return line in your function, the function will return by default whatever was the last thing calculated by it. Most of the time, it's what you want. If it's not what you want, you should specify your return specifically. Okay, so that's a function in an abstract. Let's put this kind of into practice. Here's an example. So maybe what we want is a function that will give us more detailed quantile information than the summary function gives us, and we want it to do so with interpretable names. Okay, so here would be a starting point for a function like that. Let's make a function called quantile report. I will assign to that a function which takes two arguments. It's going to take x, which has no default, so you must supply it for it to run. And it takes na.rm equals false. I'm going to use na.rm here so that we can allow our quantile function inside here to drop missing values. Okay? So the way this function is going to work is first, it's going to get some quantiles. It's going to assign them to this quants object. What it's going to assign is we're going to take the quantile function and we're going to give it our input x vector, right? Or whatever it is. We know it's going to take a vector just because quantile takes a vector. The idea here is this function input of x will just get passed down to wherever x is in the function. So if we say quantile report my vector, it's going to replace x down here with my vector and run it. Then we're going to say na.rm equals na.rm. The reason for this here is that the quantile function, if you look in its help file, takes an na.rm argument. But what I want to be able to do is I want to be able to control that dropping of missing values up here in my quantile report function. So what happens is we're setting na.rm equal to false by default. This na.rm false gets assigned to this and replaces this value down here. So by default, quantile now has na.rm equals false set. But if we change this to true up here in the function when we call it, quantile will have na.rm equals true assigned to it. This is a way to pass down an argument from this function to a function inside of it. Okay? This is an important thing to be able to do. You can play with it and see how it works. Then in the quantile function, I just have a set vector of probabilities. I want a whole bunch of quantiles. I want the bottom 1%, 5%, 10, 25, 50, 75, 90, 95, and 99th percentiles, okay? It's going to assign these quantiles of our vector x to quants, and then it just gives them some names, and then it will return this named vector. If I do quantile report on a standard normal distribution, 10,000 elements, we get this quantile report output down here. If you know the standard definition of a standard normal distribution, these are sort of the quantiles you would expect. Your bottom 5% should encompass 1.62-ish or so standard deviations of your data. Your median should fall basically dead at 0, blah, 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 right? Okay. So this is a nice little quantile function. If you had a single vector in your data, you got to get a lot of quantiles from it. Instead of having to manually do all this calculation of quantiles and assigning names, we can now just do quantile report and pull it out. Okay? Anyone have a question about this? Is this deeply confusing? We will continue to ramp up a little bit. We're not going to get as bad as we did in the loops lecture, but we'll keep doing more complex functions. Okay. Okay. So now that we've generated a function here we might want to use, I want to take a slight tangent to talk about apply functions. So looping is bad and you shouldn't do it, right? I spent an entire lecture on it and I made it difficult to scare you about loops so that you would do fewer loops. And now I'm going to show you what you can do instead of them, right? So writing loops is challenging. It's especially challenging for new coders, which is many, if not most of the people in my class. They require writing a lot of code and they're hard to troubleshoot. Loops don't look like almost any of the other R code most of us usually write. They kind of look like they're borrowed from some other language, right? And it's not that they're borrowed from some other language, it's just that convention is not good R style. Good R style is applying things. Loops, that is, are not the only way to iterate over things in R. Like a loop, apply functions will iterate over elements of objects. The difference between an apply function and a loop is that apply functions don't need all that pre-allocation. You just directly assign their output and not worry about pre-allocating things first, but they have to use a function, okay? You have to make a function call inside an apply. They can only use functions. So instead of writing a loop that has a whole bunch of code inside its body, you instead write a function with a whole bunch of code inside the function's body, and then you apply it to things. That is the proper R style for iterating. Basically, anything you can do with a loop can be done more easily with an apply function, okay? And the secret is, under the hood, apply functions actually are a loop, right? What they do is they iterate one function call at a time over each element of anything you give to them. It is running the loop, it's just taking all the hard stuff out of the way. Okay, here's an example, right? lapply takes a list and applies a function over it, okay? So lapply is really useful because, as I keep saying, data frames lie to you and are not a matrix, they are in fact a list. lapply allows you to apply a function to each column of a data frame, and it will spit out a list with all of the outputs. So if I wanted to run quantile report over every column of the Swiss data frame, I could say, I want to apply to a list. The list I want to apply it to is Swiss, and the function I want to apply is quantile report. That is the entire syntax for the lapply. And what it will do is take every column in the Swiss data set and run my quantile report function on them one at a time and automatically name the output elements, the columns of that Swiss data frame. Okay? This is way better than writing the loop, right? This looks a little bit more like our call means function or something like that. We have one simple call, it just works, it spits out what we want. But instead of producing like a single element for each column, it's producing an entire vector, which is an element of a list, as an output, okay? These apply functions are just way better than writing a loop, mainly because they're super concise. If I wanted to save this to an object instead of displaying it, I don't need to pre-allocate or something like that. I just take this statement, put an assignment operator on its left, and assign it to an object. I don't have to pre-allocate, I just assign to it, it works, okay? It's still iterating over each column of the Swiss data frame, but you don't have to specify all that annoying stuff in a loop. I don't even have to say for I in Swiss or anything like that. It knows you're iterating over every column and that you want to use all of them. It figures out the iteration for you, okay? So here's a question about this. How would you do this but select only some of the columns? For instance, you want to do this on categorical variables, so you need to select the interval ones. There's a couple different things you can do if you want to do that. The easiest way to do that would probably actually be to use like something like summarize in dplyr, which has syntax already to select columns of specific types. But I could do it with this, and let's see if I can come up with a fast demonstration. It's always fun to see if I can come up with this on the fly. Okay, so we had lapply Swiss quantile report. I don't have quantile report, so I'm going to say, let's use call means as an example. X must be an array of at least 2 dimensions. Oh, and I can't do call means. Let's just do, what would give me, what would be good to use over the Swiss data set? Summary? Okay, summary will work. So by default, summary generates essentially quantiles. So if I do lapply Swiss summary, it gives me one summary call for each one of these, right? So what would happen if I wanted to only do it over, let's say, columns 2 and 5, I'd really just subset the data, right? I'd say like 2 and 5. Then I can only do it over 205. I'm just changing the input. Now, if I want to do something like, I want to do only the columns of Swiss data which are numeric, I would have to do something like, oh, this will be funny. How about let's go, sapply Swiss is .numeric. So what this says is apply over the Swiss data frame the function is .numeric. Check each column to see if it's true or false. But I'm using sapply, I'm going to introduce in the next slides, which simplifies this to a vector. So now this is a vector of trues and falses. It would select then only the numeric columns in Swiss, send them into my lapply, and give me my summaries. Okay? So these apply functions are also useful for doing things like that, right? So instead of having to come up with some loop or some weird way to figure out which ones are numeric, I just used sapply to generate for me indices of things, okay? So this is why these apply functions are sort of ubiquitous. It's the first thing I think of to solve basically every problem that has to happen over multiple columns, rows, or elements. Okay, so sapply, the thing I just showed you in the example, is simplified lapply. What it does is it takes whatever lapply generates and tries to turn it into a vector or a matrix. The thing is lists like this are hard to work with. I scared you with lists earlier in the term, showing you they're weird objects that can store everything. So instead, you might want an output that's a matrix or something. Here, sapply takes the Swiss data set, it generates quantile report. It then checks to see that the output of these are all the same length. If they are, it binds them together into a matrix. That's all it does. So instead of spitting out a list, it takes the same output and makes it into a matrix. What you see here is each column of the Swiss data set is a column in this sapply output, and each row is a different element of that quantile report output. Okay? So this is nice. This produces sort of a summary table that's in matrix form for us. Sapply, this is great. This is way better than doing something with a loop. The loop equivalent of this would have been to go over each one of these variables, iterate over them, and assign to a matrix the output of it to each row, right? And then you have to get the names right too. It'd be a pain to do. sapply simplifies the whole process. Okay. There's also a generic apply function that works over any object in R. Apply, you say, give it an object you want to apply over, and then you specify the margin. The margins are just whatever dimension you want to go over. The first margin is rows. The second margin is columns. If you have 3 dimensions, the third dimension is depth, right? So this works over arrays and stuff. Here I say apply to the Swiss data set over its columns the function quantile report. You'll notice the output is exactly the same as sapply, because sapply is a shortcut for this function call. Okay, so here is a question. Can you swap the rows and columns on sapply? No. The reason I can't swap the rows and columns is because a single element of a data frame is a column, and sapply by default goes over the elements of an object. If I want to swap the rows and the columns, I would have to apply here and say margin equals 1. Or there is a thing you could, that'd be it. Or what I could do is I could take Swiss here and transpose it and then put it into this sapply. So instead of telling sapply to go over rows or columns, I could just flip the rows and the columns in Swiss. Yeah. That's the base R way of doing all of this stuff. So before all this tidyverse stuff, what all us R programmers and stuff we're doing everything with apply commands and just sort of flipping inputs, outputs using base R syntax for all this stuff, okay? And you'll probably notice, or maybe have thought about this already, the main package for data manipulation we're using is called dplyr. It's data frame applying. It's actually based on the principle of all these apply functions, but it's data frame specific. It is descended from another package called plyr, which was a package designed to simplify apply calls, okay? So these apply calls are sort of the origin of all of this nice tidyverse syntax we're now familiar with. This is the history of it, and they're still terrifically powerful. And this is also considered good R syntax or good R style for writing things, okay? Okay, so you might have remembered We used a loop to load in a whole bunch of CSV files last week, right? To do this, what we had to do is get a list of the files in a folder, assign them to a file list, construct some file paths. I made nice names by removing .csv from them. I pre-allocated a list to store all these data frames. I gave it some names. I ran a loop that says for I in sequence along our file list, we read in each file and assign it to the appropriate element of our data list, right? And then I take my data list, bind it together into my complete data set, and I show it. So this was a loop way to read in a bunch of CSV files. If I had 1,000 CSV files, this would still work. This is fine. It's not super complicated, but it's not the prettiest thing in the world, right? The way I would actually load in a whole bunch of files is not with a loop, something I hinted at, I think, in that lecture, and I definitely probably mentioned in lab. Instead, I could use an lapply function to iterate over those file names and then bind them together. This beats writing a loop. I say, I want my complete data to have assigned to it lapply over my file paths. So this says, take all my file paths, run read CSV on them. So it's going to take each file path one at a time and run read CSV on it, run all of them one after another, stick them together into one big list because it's an lapply. I can then pipe the output of this into bind rows, and I get my complete data with the entire loop style thing and the binding of rows done in one quick call. Okay, this is way easier to read than the loop. It's way easier to write, and it's actually faster too. Not by a lot, but it's a little bit faster than the loop. Okay, so this is how I would normally load in my data in the loop up until about a year ago, where a vectorized file reading function appeared in the vroom package. Vroom is a tidyverse package that is not yet installed with tidyverse, but it makes loading files in really fast and stupid easy. So the fastest way is not to use a loop. It's also not to use lapply. It is instead to run a purely vectorized function. To do this, I could load up the library vroom and literally just say the vroom function and all of the file paths as a vector. It will read through every one of the file paths and automatically bind the entire thing together into a data frame on a single function call. Vroom will also read in your CSV files between 10 and 1,000 times faster than read CSV. Vroom is very, very fast. If you need to load in CSV files quickly, use vroom. It's the fastest package out there. It's also super easy because you never have to apply. You just give it a whole directory, spits everything out. Okay. Another nice thing here is this file path here could be tab separated files, CSV separated files, dash separated, whatever. Vroom will figure out that delimiter and load them for you too. So I only have to say read CSV. It will figure out what the files are and read them properly. So vroom basically could be your one-stop shop for loading files. It does not, however, have that diagnostic problems function read_CSV has, so I don't teach it as the primary way to read files. Later on, when you're working with big files, this is your friend. Okay. So the thing that I sort of said is that loops are the proper way to iterate over things. With regard to that last slide, file paths is a vector of file names. It's a vector of file paths. So it's not just the file names, but also the folder that they're in. But yes, if your working directory was the same directory that all the files are in, you could just give it the file names. So yeah, that's this could be a vector of like length, and I actually used vroom for this. This could be a vector of like length 2 million. Like I did a file load of 2 million CSV files a little while back, and I did this with vroom, a single call like this. It loaded all 2 million files and did what I wanted it to do. Vroom's pretty cool. And it did it crazy fast. Anyway, so yeah, like I said before, basically any loop could probably be replaced with an apply function. So a sort of generic way to approach this, if you want to replace a loop with an apply, is this. So figure out what it is you iterate over in the loop. For instance, you might be iterating over a sequence along X. Maybe it's the numbers like 1 through 10 over a length 10 object. Maybe it's the actual object itself. whatever you're iterating across. So not like the I, but the in. So if you have a loop that's like for I in 1 to 10, this is the 1 to 10. This is going to become the first argument of your apply function. Then the body of the loop, all the code you had inside that loop can basically be copy pasted into the function you're going to run on lapply. And it will just take as its input whatever you iterate over. So that was the I in your loop, make that the input to the function. Then just run your lapply and assign its output to whatever you stored the loop in. And you'll magically find you now have a lot less written code. It's easier to debug, and it probably just ran 5 times as fast as your loop. Okay? Basically, any loop can be converted to an apply function. There are some something that refers to the previous iteration. If you need to refer back to a previous element, it won't exist yet until the whole thing is run, which means under the hood, things like Markov chain, Monte Carlo and stuff are run using loops. Okay. Okay, so back to making functions. So here's an example of something we might want to do. We might want to discretize some continuous data. That is, we've got some kind of variable like income, and we want to group it up into buckets and make an ordinal variable out of it or something, right? Normally, it's not good to discretize data. If you have continuous data, it should probably stay that way. But sometimes you'll have a boss, superior, somebody like that will be like, I really want you to make categories out of things. And in your head, you can be like, you're wrong and we shouldn't do that. But then you can do it anyway and write a function to do it. Okay, so if you want to know how to do that, we can write a bucketing function. So there's already a function in R called cut that will divide things up into buckets. But cut requires you to tell specific cut points in your data. Like you got to give it the numbers you want to cut at, or tell it the number of buckets you want to cut it into, like 5 to give you 5 buckets. We might not want to do either of these things because as programmers, we are lazy people. What we're going to do is we're going to make a convenience function that will call cut under the hood in there using quantiles to split things up, and it will return an integer. That is the bucket that variable or that observation is a member of, okay? So this will take some continuous variable and make an ordinal variable by dividing it into quantiles. I don't know why the theme for today is using quantiles for stuff, but it was when I wrote this. Okay, so we're gonna call this function bucket. We are going to assign to it a function which requires the argument x. I'm going to assume it's a numeric vector. We could make it take something else. And by default, it's going to cut things up by the 33.3rd percentile and the 66.7th percentile. In other words, it's going to divide it up into 3 even buckets by default. But we can change it if we want because it has this as an optional argument. What we're going to do is we're going to first set a low extreme value. That is a value that will capture everything at the bottom end of our data. Some quantiles where we want to cut it, and then some high extreme to catch everything. The idea here is the cut function here. You got to give it a minimum where you want to start cutting things. We don't want to drop data. So what I'm going to say is I want the breaks for this. That is the breaks where we're going to divide our data up to start at the minimum of x minus 1. Well, the minimum of x minus 1 is a number that no matter how small x gets or how low it gets, will always be below every value of x. In other words, we're going to make sure the first cut point is lower than the lowest value of x so we don't throw anything out. Okay? Then what I'm going to say is all the other breaks, that is all the places we're going to divide these buckets up, are going to be quantiles of that x vector whose probabilities are defined by the quantiles of the function. So I could give this the same vector of quantiles I used in my quantile report function before, and however many bins there are from that, you would have that many buckets that get spit out, okay? So by default, probs here is going to be 0.333 and 0.667. So this argument by default gets put here. And then I just say, go all the way to the maximum of x and 1 higher, okay? Yeah, and yeah, so Kelsey, that's the answer. Why isn't it just minimum of x? because it is a non-inclusive cut, if I give it the minimum, it would cut off the lowest value. So the way these breaks work is the breaks would chop off anything that lies exactly on them. So I just say go a little bit lower and a little bit higher. It's just the syntax for quantile, or not quantile, but the syntax for cut. And then what I want to do is this function should return to me the result of calling the cut function on my x vector where the breaks are equal to the breaks I just created. And I say labels false. Labels false makes cut return a integer vector of the like buckets it gets put into. If I say labels true, it would return the quantiles instead. Okay, so we've got this bucketing function. This is a little odd. This might be a little confusing and hard to follow, but let's see how it works. So what I do here is I generate some random data, 100 observations from a standard normal distribution. I'm going to assign to bucketed random data the result of bucketing our random data with these quantiles. These quantiles are the 5th, 25th, 50th, 75th, and 95th percentiles of my data. And then I just plot it. So on the x-axis is my buckets of my data. See how they're in discrete units, bucket 1, 2, 3, 4, 5, and 6. And then the original random data are on the y-axis. So we can see that bucket 1 looks like it goes up to, I don't know, about negative 1.62 or something right here. I know that because it's a standard normal distribution. And then bucket 2, bucket 3 is right around the median mean of the standard normal. Then 4, 5, and 6. Okay, so this converted a continuous variable into a ordered discrete variable. Okay, and we know it works. So if you want to bucket something and you want to do it like algorithmically, maybe you got to do it to a lot of columns or something, or you got to do it repetitively, you can use a bucket function like this, and it beats manually typing in and calculating these things every time you got to do it using cut. Okay? Questions about that? It's not my favorite example. I think I'm going to replace bucket next lecture with something more entertaining. Okay, chug along to something that's actually more useful. So here's another example. Maybe you've got some data set where you know there are impossible values. So this is really common if you get like survey data and you know you shouldn't have any sexual frequencies of 999 in a year. Maybe somebody's really going at it, but they probably shouldn't be 999 times. That's how chafing occurs. And you want to remove these sorts of values from your data, right? Another example here is I've created some fake school data. These school data have a school labeled A through J, and then a percent, or rather a proportion passing exam, and a proportion on free lunch. Well, properties of proportions, they should be bounded between 0 and 1. So they shouldn't have negative 1s, and they shouldn't have 99s or negative 13s and stuff like that, right? These data are probably data that either had a data input error, or these are supposed to be missing values of different types, special codes, right? This is really common in survey data, but sometimes administrative data has it too. We actually had a problem like this in some Seattle Police Department data they gave me a while back, where they hadn't realized that when they migrated from their old record management system to the new one, it coded all missing values for the type of Terry stop it was to dispatcher initiated. So this is a problem because my job was to determine if there was bias in dispatcher and officer initiated Terry stop. So I did a whole lot of work before I discovered that there was something fishy about that. Then they got to pay me more money to continue doing it. So it actually was a great problem with missing data. But still, these things happen. Pay attention to what your missing values are. Hope they aren't recoded as something valid. Okay, so we have data like this. What we want to do here is we want to have some function that will automatically look through these variables and replace these invalid values with NAs and keep everything else the same. So the goal, right, is to take as an input some vector x, which is numeric, have a cutoff for low values and a cutoff for high values. That is, delete everything below the low and delete everything above the high. Its output should be a vector with NAs in those extreme places, right? We take in some data, we get rid of the things that should be missing values. Here's a function that can do that. So I'm going to call this function remove extremes. And so a theme you'll notice for writing functions, name your functions, like other objects in R, descriptive things with long names. This keeps you from overriding existing R functions and also keeps you from looking down your data set and wondering what function 1 does in your script, right? Don't like var1, var2, function 1, function 2, or my function and stuff like that. Anyway. So we're going to write a remove extremes function, which is going to be a function which takes x and requires a low and a high value. It has no defaults because who knows what kind of data we're giving to it. We don't want to make assumptions, so you got to provide them. So the way it works is we're going to assign to x no low the result of if else x is less than our low value, NA. Otherwise, just give me x. So the idea here is this is going to check to see if any of the values in x are below our extreme low. If they are, assign an NA here, but otherwise leave x alone. So x no low is just x with no low values left. I'm then going to create x no low, no high, which is the result of if else x no low is greater than high, NA, otherwise x. Do you see something funny about this statement? Does anybody see it? What am I not removing from this, or what am I using to assign to x no low, no high? It's me taking advantage of some odd R behavior to be lazy. So you'll notice I'm assigning if any value of x no low is greater than high or not greater than high, assign x. Notice I'm not assigning x no low, I'm assigning x back. So you would think that this would reassign all of those values that are low, because I'm not specifically excluding them, right? But it doesn't, okay? What's going on here is these have been replaced, these low values have already been replaced with an NA. What does a logical statement produce if you test to see if an NA is greater than high over here or some number? What does NA do to logical statements? Nobody?
Produce an NA?
Yeah, it produces an NA. So that means I don't have to return x no low over here. I can just return x because these NAs in x no low will also return an NA. It's a stupid programming trick. You might want to instead put x no low here, but just to let you know. Usually somebody asks me a question about why I did this, so I just preempted it and said it. Okay. And then we will return x no low, no high, which is our original x with all the low values and high values removed. So I can take my school data proportion passing exam and say, it's a proportion, there should be nothing below 0 and nothing above 1. I remove extremes on it and I get all my proportions stay intact and my values that were impossible are replaced with NAs, okay? So now I have something that will filter out missing data for me or replace values that should be missing with what R recognizes as a missing value. So if you want to apply a statement like, or apply a function like that to multiple columns in your data set, we could do it with lapply or sapply or whatever like I showed earlier. But you can also do it in dplyr using mutate at or summarize at, or in the new dplyr 1.0 that just came out, the across function. So the way these functions work, mutate at and summarize at, which I showed in week 3, they take an argument of functions. What you can do is you can say, I want to run these functions on some set of variables, and it will run whatever function you give it on every variable selected, okay? So what I want to do is I want to apply our remove extremes function to both of the numeric columns in this data set, that is to everything but the school column, okay? I could have also said mutate if is numeric, but instead I say, I want to take my school data and then mutate at I want to mutate these variables. I'm saying everything but school. What do I want to do to everything but school? Tilde, because this is the syntax for mutate at. This is basically a formula saying I'm going to do the thing on the right side of the formula to this thing over here. The thing I'm going to do to all these variables here is remove extremes, x equals period. Period, if you remember, it says send the data here, kind of. In this case, it's sending the individual variables there. Then it says the low value is 0 and the high value is 1, the same arguments as before. The output of this is my entire school data frame in its original format, but now the 2 columns we selected, that is everything but school, have the NAs removed according to the rules I used in remove extremes, okay? So this is a way to take a function we wrote, which is vectorized and nice and easy to use, and apply it to multiple columns in a dplyr style pipe chain. So this beats writing a loop, but this also beats writing an lapply type statement. We can just nest this in with all of our other code and it just does it. So this is the utility of writing your own functions. This would be a big pain to write this thing into a mutate statement and put all of this remove extremes code in there. But if we write the function outside of it and then call on it here, we can just do it inside a pipe chain. Any questions about that?
Yes. So in the function remove extremes, is it actually creating an object or destroying an object, or is it just producing one of those kind of like temporary ephemeral R type objects? So for example, if you wanted to have X, the data that you're putting in to remove extremes, and you want to remove all of the extremes and you want to change the input, do you have to assign X to remove extremes X? Does that make sense?
So what I would have to do here, if I wanted to remove if I wanted to remove all the extremes in this data set, I would have to assign this back to school data up here at the top. If I wanted to do it down here, like remove extremes, school data, $PR passing exam, I would need to put this on the left side and assign to it also. So remove extremes will run it, but because I haven't assigned it to anything, it just displays it in the console. If I want to make the changes to this thing, I would have to assign to it.
Is it bad form to have, or can you even have a function create a new thing, a new object?
You can do it, but it is bad form and it's surprisingly awkward to do, because you'll notice, see how I'm doing assignment operations in here in the function? Okay. These X no low, no highs will not exist after I run the function. Anything created inside the function doesn't exist outside of the function. So if you want to create something like do an assignment here and have it appear in your global environment, you can't do a normal assignment like that. You instead need to call on an assignment function directly, and that function is actually called assign, and you have to tell it to assign to your global environment. This is considered very bad R style and actually bad software development style. It's something called having side effects in your function, and it's considered one of like the 7 deadly sins of programming. So normally you don't want to do it. You want to always explicitly assign by calling the function and assigning its output, rather than calling a function which assigns silently into your global environment. You can do it though, and sometimes you'll see especially old school self-taught R programmers doing it all the time, but people who've been formally trained in it or have learned modern R style wag their fingers at them. But if it works for your application, what it comes down to is if it's the best way to do something, you need to do it that way, do it, right? There's also a supra assignment operator, which is assign like this, but with 2 less than signs. And that will assign to the environment above the one you're in, and that would assign to the global environment here. But for the love of God, do not ever use that operator. I'm telling you about it that it exists, but don't do it. It can cause a lot of chaos. Okay. You'll see it sometimes used inside packages though. Okay. Yeah. Great questions though. I love it. Yeah, it's good to understand the mechanics of this. So R, you basically always should be manually assigning if you want to overwrite something or make changes to it. This is very different from some other programming languages. Some programming languages and even some approaches in R, like data.table, does a lot of modification in place. so you can actually modify and do edits to data without doing assignment. That's a different style. I don't like it, and a lot of people don't, but it has some massive advantages in speed, so sometimes there's reasons to do it. Yes, that is definitely chaotic evil coding. There's been a couple packages released that are purposely nefarious packages you can download for fun to see exactly how badly simple functions can screw up your R. And one of them is a function that when you call it, it will call back up to the higher environment and globally reassign true to false and false to true silently, thus flipping every Boolean statement, in R. And then it also overwrites the assignment operator, so you can't undo it. And so the only way to do it is to like close out your R and wipe the environment stuff. Little fun things like that. Chaotic evil coding for sure. Okay, so something I want to say. Standard and non-standard evaluation is something I brought up a little earlier in the term. Okay, if you're coming from a different programming background, you're not just learning coding in R, this has probably been driving you insane. If you came from a programming language like Python or something, where you usually have to have inputs in quotes, you're probably confused by why we're never quoting anything or randomly quoting things in R, okay? So dplyr and all the tidyverse use this thing called non-standard evaluation. It's what lets us refer to our variable names without quotes in them. So over here, you'll see I can just say school. Over here, I don't have to put school in quotes. This is weird in the programming world. Normally, if you give an object as an argument, you're actually going to put it in quotes here as an argument, and it will go find that object in school data, because this isn't really the object school. This is really the name school of a variable in school data. If you think about it too much, it starts to become very confusing what's going on here, especially if you've programmed in other languages. This is called non-standard evaluation. In dplyr verbs like mutate have recently started supporting standard evaluation, which allows you to use quoted object names the same way we've been using unquoted ones. So for instance, I could say Swiss select fertility and Catholic in quotes, and it works just as if I didn't quote them. For real world programmers, software developers, this is actually even more confusing because now it works either way that you do it, and side by side you could have one quoted one and one unquoted one, which is really weird, but it just works. The reason for this is because in something like a loop or giving arguments to a function, it's much easier to pass a quoted thing than an unquoted object. We're going to see this in a little bit when we write some ggplot templates. So just know that you can give a function like select quoted or unquoted names and it will work. Some things will not work this way, like ggplot, you specifically have to use a different set of functions if you want to give them quoted names, which we're going to use in a bit. Okay, so if you're in this situation where you think to yourself, it's real easy to pass either a quoted name or only an unquoted name, and you normally would do the other way, Google stuff on standard and non-standard evaluation. So here's a question. How does this work when you're using dplyr within a function? If you want to send like a variable name, say to select, and you're using select inside a function you wrote, I would pass down the quoted variable name instead of the unquoted one, because it's going to do some weird shit if you try and pass down the unquoted name. You can experiment with it and see, but normally it's much easier to write functions that use these quoted variable names and quoted arguments. In fact, I would highly recommend that unless you're directly working on the object, you use quotes for your argument names. We're going to see kind of a little bit of that in a second. Okay. So another thing that you can know in dplyr is using anonymous functions. So you can skip naming functions altogether in dplyr and also in apply functions if you're not going to use that function again. So for instance, the code below here will take the mean of a variable and divide it by its standard deviation and return that. This is called an anonymous function. This whole thing over here is actually a function being run on your data, but I haven't assigned a name to it. I've just called on it. What this actually means is every damn time you did some sort of dplyr syntax that has on its right side a mathematical operation or some function calls, you were actually already calling anonymous functions. You just weren't naming the operation you were doing, okay? In some programming languages, it is not possible to do these sorts of statements over here, or you have to do them in a specific syntax. That's referred to as lambda functions. If you go to another programming language, you may have to set them up in a different way. Okay, but for us, it just appears to work because of the magic of dplyr. Okay, the equivalent of doing this says take the Swiss data set, summarize every column in it, and get its mean divided by standard deviation. I could do this exact statement with an lapply like this. But notice here, I have to say, take the Swiss data set and run a function on it. And the function is take the mean and then divide it by the standard deviation. dplyr allows us the shortcut of not saying function of x, because by default, dplyr takes on the right side function of period. It's just the way that it works. It works silently for us, and we haven't known it's doing magic behind the scenes, but that's what it's doing. If you want to use it in an lapply, you actually have to write a function in line like that. Okay. That's all I'm going to say about anonymous functions. So I'm going to go on to the next example here. Let's say what we want to do is we want to make ggplots look a particular way. These aren't the prettiest looking plots, but maybe you're a picky person and you like your plots to look exactly one way, always that way, and you're tired of constantly writing all of your picky person code all over your script files, okay? A good thing you could do is write up a template or a function that generates ggplots given parameters, so you don't got to retype any of this code over and over again. So what I have here is I've loaded up the Gapminder data from way back in week 2 and homework 2 and ggplot. And what I've done is I've done a plot where I say I want a ggplot of the Gapminder data filtered down to Afghanistan. On my x-axis is year. The y-axis is population in millions, so population divided by 1 million. I want to draw a line through these data, which is fire brick red. I want no X label. I want my Y label to be population in millions. My title is Population of Afghanistan since 1952. I apply a minimal theme to it, and I adjust the plot title to be, left justified and size 20. Okay, so this is me being picky about a bunch of things. So here's a question. How could we make this up here flexible for any country? What would have to change every time I call this thing if I want it to work for any country? Anybody have an idea?
The country equals?
Yeah, so filter country equals Afghanistan would have to be replaced with something that can change. So this could be all this could be wrapped in a function, and then I'd have to say like country equals country, the variable, so I could pass to it whatever country I want. But what else needs to change in here for that to work? Oh yeah, I see in the chat. The title. So instead of saying population of Afghanistan since 1952, we want to be able to pass this plot any country name we want and have it change how we're filtering it and how it generates the title. So two different things need to change. Okay. Next, how could we make this flexible for any Gapminder variable? What would we have to do? What needs to change? We're ahead of schedule, so I'll wait. Yes, the Y variable. So up here, the variable we're using in Gapminder is population, right? Well, pop up here, in fact, pop divided by 1 million, that needs to change. We need to make it so that this thing is now flexible to take any variable. And then down here, Kelsey says here, the X, the Y, the labels, and the title. So let's just say that we want to leave year the same. Let's make them all over time. We could make it so it could do either of them, but I'm just going to say let's make them work all over time. So we need to make it so this Y over here is different. And then like she says here, the labels. So Y label population millions. We don't want to be population millions. We want to be whatever variable we're working with. And then also the title needs to change, right? We need to say, instead of population, we need to be able to say something like life expectancy. So we're going to be something like variable of country since 1952 or something like that, right? Technically speaking, we could even make it flexible for filtering to countries if we really wanted to also. Okay, so yeah, that's a lot of stuff we want to change. Okay, so here's an example of this plot. This plot looks something like this. This is population of Afghanistan since 1952. It says population in millions over here. What we're going to do is we're going to write template functions that will allow us to just give a function a country and a variable and have it take care of the rest of the drawing of the plot. Okay. So we want the same function given this is Afghanistan and population. We want to be able to say give it life expectancy and Peru and draw this plot for us. We don't want to specify anything else. We don't even want to tell it what data set to use because we know it's Gapminder. Okay. So here's an example of making country flexible. What we want is we want the user, that is you if it's for you, we want the user to be able to input a character string for country as an argument, and it will get the subsetting of the data and the title right. So what we did is we basically took all of the ggplot code we did before with a couple modifications, and we've stuck it in a function. We're going to call this function Gapminder life plot. In this case, I'm going to leave it only for life expectancy, but we're going to make it flexible for variables after this. This is a function of country. For now, it's only flexible for country, so it only needs one argument, the country. What it's going to do is say Gapminder and then filter so country equals our country input variable. So if I give this function Peru, it's going to put Peru here and filter our data to Peru. Okay. It's going to keep year and life expectancy as X and Y. It's going to stay fire brick red with no X label. Y label is just going to be life expectancy. It's not flexible for variables yet. It's still a minimal theme. But then the thing we have to change is the title, right? What we need is we need to be able to take this input variable and stitch it into the old title. So for that, we're going to use the paste function. I'm going to say the title for our plot is going to be some text we paste together. It's always going to be life expectancy in, because that's a life expectancy plot, but it needs to be flexible for country. So whatever country we give it, it's going to say life expectancy in Peru, life expectancy in Chile, life expectancy in South Africa, whatever. And then it's always going to say since 1952, because we're not messing with the years and the Gapminder data starts in 1952. The rest of it is the same, right? Let's use this function. I can now say Gapminder life plot country equals Turkey, and it generates a life expectancy plot for Turkey that looks exactly like our prior plot, but the only thing I had to type was Gapminder life plot. Technically, I don't even have to specify that argument. It only takes one argument. I could just say Gapminder life plot Turkey. Okay, so this is something kind of nice already. You could do something like build a dashboard out of this that browses through countries or something like that and just changes the plot by changing a single input to a function. Or you could have some big data set you work with routinely and you just want to be able to see all the different countries called up rapidly. You can just be able to type the country into this function. It gives you the plot you want, right? This saves you typing all this other extraneous garbage we don't like repeating all the time, right? Okay, any questions about that before we get more complicated? Not too bad. Okay, let's make it a little bit bad then. Okay. So the next thing that we want to do, right? We want to be able to make that y-axis variable flexible. We want to be able to select any of the Gapminder variables except year, right? So those are life expectancy, population, and GDP per capita, right? The thing is, though, is that if you look back at how this plot is generated here, we have a variable name like life expectancy over here, and then we have life expectancy in Turkey since 1952, okay? The thing is, though, is that it might be better to say something like, instead of population in Turkey, it might be able to be nice to say population of Turkey or GDP per capita of Turkey, but life expectancy in over here. And over here, life expectancy for population, we might want it to say population in millions or GDP per capita in dollars. So we want different text for the variable to appear up here in the title than appears over here in the y-axis, okay? So to do this, we're going to use something called a simple lookup table. If we use Python, this is analogous to using dictionaries for the same sort of thing. The idea here is that we want to be able to give a single variable name, the actual variable that exists in Gapminder, to our function and have it go and look up a proper y-axis label and a proper title text to generate it. So the way we're going to do this is we are going to have a named vector. This here says there is some text, life expectancy, which is named life exp. So life exp is the original variable name in the Gapminder data. If I subset y-axis label to be life expectancy, life exp, it's going to spit out the full life expectancy text. You can see that down here. This y-axis label that has this whole named vector, if I say y-axis label, subset it to pop, what actually spits out is population in millions. This is the actual label I want on the y-axis of my plot, right? Notice though that if I subset my title text by the exact same pop, what appears is population of. So with the exact same variable name, I can get two different outputs out by using these different named vectors. This is a way that I can have us pass to this function an actual variable name, but generate nice y-axis label text and a nice title text. Okay, let's see this all in action. So our plot code just got pretty big because the idea here is to use these lookup tables. We need them inside the function so a user doesn't have to go and create a lookup table ahead of time, right? There's one other complicated thing other than this lookup table that we're going to have to do. We're going to have to tell ggplot we want to be able to give it quoted variable names instead of the raw variable names. I'll show you that when we get to it. So what we're going to do is we're going to create a new function called gapminderplot. This is a function which takes two arguments. It takes a country and it takes a y variable. It doesn't need any other arguments. It knows the data set. It knows how to do all of our styling and everything. It just takes these two. The way it's going to work here is it's going to take this lookup table I created before. That is, it has values of life expectancy, population millions, GDP per capita USD, with names equal to the variable names in our data set. It has this lookup table, and we immediately subset it to our current y variable. So if I say gapminder plot life exp, it's just going to assign to y-axis label life expectancy the text. If I say yvar equals pop in quotes, it's going to see pop and assign population millions to y-axis label. If I give this function gapminder plot GDP per capita, it's going to assign GDP per capita USD to y-axis label. So it uses this lookup table and immediately assigns it to y-axis label. It does the exact same thing for title text. If I say gapminder plot life exp, title text is going to be life expectancy in. If it's pop, it's going to be population of. If it's GDP per capita, title text will be GDP per capita in. Okay, so this automatically assigns a y-axis label and a title text before it begins drawing the plot. Okay, then it's going to say ggplot gapminder filter, again, country equals country. This is the same code we did in the prior plot where it knows how to filter down to the proper country. But I do one additional thing. Because I know I want my population to be in millions, I go ahead and mutate population in millions, whether or not I'm going to use it. If I do call on population, it's been pre-mutated, so it's ready to go. Then we introduce a new function you have not seen before in this class. AES underscore string is ggplot's AES function specifically for use in writing functions. What this AES does is it works just like the normal AES function, except you can give variables as quoted variable names. You only really ever need to use this when programming. So here we can say yvar in quotes, and it will pass down like y equals pop in quotes, and it will actually be able to grab the correct variable instead of plotting the text pop as your y variable, which is a common mistake I saw on the last homework. Okay, so we have to use AES string because this takes standard evaluation instead of the nice non-standard evaluation we're used to using in ggplot. Then we do one extra special thing. Our title is almost entirely created by stitching together new information. We're going to say the title of our plot is equal to title text country space since 1952. So this means if the variable we give to Gapminder plot is GDP per capita, the title is going to be title text is GDP per capita in country, let's say it's Afghanistan, is Afghanistan since 1952. So the whole title gets stitched together dynamically. Okay, that is the entirety of what we have to do to make this function flexible for country and for y variable, at least those 3 y variables. So yeah, it was more work than if we had to do it like manually. But if you had to generate a lot of these plots, or you wanted to make it easy for a user to generate these plots without giving it a whole bunch of information, this plotting function will handle it for you. Okay, so this is how it works. I can say Gapminder plot, country is Turkey, y variable is population, and it now says population of Turkey since 1952 with population in millions. Okay, do I have another example? Of course not, I forgot to put in a second example. So I could change this thing arbitrarily. You know, I could say over here, South Africa, GDP per capita, we get a nice plot of South Africa's GDP per capita over time. This is a way to create a complex, relatively complex templating function for ggplot. We no longer have to do anything specific, it just generates plots for us. Okay. If you do things like program dashboards for users, you'll probably do a lot of this sort of thing to call on plots of a specific type rather than manually writing lots of code. Okay, any questions about that section? Okay.
For the title text, did you add spaces after so that you wouldn't have those two variables smushed together?
Yes.
Mm-hmm. Got it.
Exactly. Yeah, so over here you'll see like the title text, it's life expectancy in space, and then the country name doesn't have any spaces in it because you provide the real country name, and then this is space since 1952. It takes care of the spacing. Alternatively, I could have left the spaces out and said normal paste instead of paste 0, and it would have worked. Okay, so Kelsey's got a question here. Can you explain AES string again? I don't quite understand, which is quite reasonable because it's kind of weird. Okay, the idea with AES string is that with our normal AES function in ggplot, you would be able to say x equals year without any quotes on it, and y equals, say, GDP per capita without any quotes. To make ggplot understand year in quotes, you have to use AES underscore string instead. This is aesthetic AES, which accepts a string as an input instead of an unquoted variable name. Does that make sense? You can't just normally give AES and ggplot year in quotes. Otherwise, it thinks you actually want to plot just the text year. It won't look for a variable. It's a finicky thing, but there's good reasons in ggplot not to make it accept either quoted or unquoted ones, because sometimes you actually want to provide a vector of like, directly provide like a vector of character data there as a factor or whatever. Okay, anything else? Okay, the second part of your homework for the 2-part homework that's coming up will involve making a templating function like this in ggplot. It'll be a little simpler than this, but it's pretty similar. Okay. So some other things before we get finished. If you wrote a function and it is not working the way you want it to, and the error messages don't make any sense, R has some built-in debugging functionality. You can say, debug the function that you wrote, And what R will do is as you run that function, it will go through each line of code step by step as you run it. So instead of just running all the code in the function at once, it will walk through all the internal code so you can see where it breaks. Most of you, this will not be useful to you, at least not anytime soon, but know when you get to more complex stuff, there is a debugger. Often, more importantly for everyone, know that for the entire time you use gapminder plot after running debug, it will be stuck in this debug mode, running its contents one line at a time. If you want it to stop doing that, you have to say undebug the function you're debugging, and it will stop doing that. Okay. Debugging mode is a little bit more advanced, but it's nice to let people know it's there. Often it will not help you diagnose something, and the better way to do it would be to have someone else review it or try and break it outside of, run the code outside of a function. If it runs outside of a function and not inside the function, that can be hard to diagnose. Okay, so I want to go back to the thing I started talking about, or I talked about at the beginning, on sort of the process of doing any data processing or programming thing, right? So if you're doing any kind of work with data, writing some simple software, and that's really what we're all doing, is we're basically writing software, right? There's many valid ways of accomplishing that task or approaching it. I have my general approach that I follow and I think is a good general approach. And it's very general. It's not being like I have a special method that you should all use or something like that. But I just think this is a general approach to thinking about your problems that might help you get through things. So my approach is this. Before I start writing any code, I look really carefully at my starting data to try and figure out what I can get from it. There's no reason to start working on something if the thing you finally want out of it is actually impossible to get in the first place. This is something really common with new, exciting research projects you start. You have some cool data set, you want to do something neat with it, you haven't thought about it deeply enough to realize that no matter how much you work on it, you just can't extract that blood from the stone. The information you want does not exist in the data set. This happens to me all the time. I find some great data set and I just can't get the information I want out of it. That's fine. It just means you either need a different set of data or it's an unanswerable problem for now. That's okay. But don't waste lots of effort trying to squeeze that blood out of there. It's just going to hurt you, right? So if you can get what you want out of it somehow, you can move on. Next, you need to determine precisely what you want your end product to look like. And when I say precisely, I mean really precisely. What columns is it going to have? What are those columns going to be named? What are the rows going to look like? What's in each cell of the data or whatever like that, right? You should know exactly what you want the end product to look like. Because if you know what the end product needs to look like, you're going to know the sort of functions you need to run to arrive at that object, right? If you know it's going to be a data frame, you can probably use all these nice dplyr tools you're working with. But if you know it's going to be some weird irregularly shaped object, like some kind of weird list thing, you already can take off the table most of the dplyr type stuff we've worked with in this class. Instead, you're going to have to work with sort of like lapply stuff. Maybe you're going to have to go teach yourself purr. But on the other hand, if you think about it hard enough, there might be a way to do most of it in dplyr before you get to that other set. Another thing which I don't get into in this class is it's actually possible for dplyr to work with lists inside of cells of your data frame. They're called list columns. We won't really get there at all until a little bit in week 9. Next, identify the individual steps needed to go from step 1 to 2. How do you take your starting data and get to your end product? And I know this kind of sounds like that classic cartoon. It's like how to draw an owl, begin by drawing some circles and then draw the rest of the fucking owl. But still, you know, it's like there is something to this thought process, right? It might be hard to figure out the individual steps, but if you draft these things and think about it hard, you at least have sort of a jump than over like blindly trying to type through. This is what typing looks like according to Hadley Wiggum. You type through like this and you get some sort of result, right? Okay. Then make each one of these steps that will take you from your starting data to your end product its own set of functions or function calls, right? If any one of these steps is confusing or complicated, you need more steps. It's okay to have lots of steps if it's readable. Don't try and compress things into a tiny amount of space because you like it to be elegant. It's a waste of your time. It's much better to have really clear steps and many of them than to have opaque steps that are hard to write. Okay, so this is actually what we've been doing every time we do anything in this class with dplyr, right? I begin with a data set, I tack one function onto it that gets us a little closer to our result. And I keep tacking on more and more and more and more steps. And at the end, we get some sort of result. Maybe sometimes I create an intervening object along the way or something like that, but all I'm doing is step by step by step, right? If something is confusing or complicated for you, you need more steps. The more time you spend in R, the fewer steps you sometimes need. You know how to make really big jumps. But for the most part, people in this class start with baby steps. Do simple, small operations one at a time, because having your code be understandable and readable to you is what's important. Next, once you've identified the steps, the discrete steps, do every single step separately and in order. Do not continue on to one step until the prior step is doing exactly what you need it to do. It is a waste of time to move on to the next step if the prior step isn't doing exactly what it should. And then do not worry about combining steps for efficiency until everything in the entire process works, right? It's okay if you generated some complex set of functions and they take like 3 minutes to run if they run. It's okay, right? If you only need to run that thing once in a while, 3 minutes might not be that bad. Don't waste huge amounts of your time prematurely optimizing your code. I do it sometimes, it's a waste of my time, but I'm obsessive like that. But I've probably spent more time optimizing many sets of code in my projects than was saved by optimizing the code, okay? Most of the time, your code is fast enough to do the job. If you're getting to the step where something's taking like hours to run and you know it's inefficiently written and you're gonna run it a lot, yeah, optimize your code, but write the bad version first and then figure out what's slow about it. Don't try and make it fast step by step unless it's something that won't run at all until it's super fast, which is common with big data. A lot of these steps throw out for big data stuff. Big data is its own animal. Okay. Once you're finished, if you got to do this again, convert the prior steps into functions. Maybe convert the entire thing into functions. So I have a couple projects where there's a single function in the entire project, which downloads the data, cleans the data, runs the models, does the visualization, and generates the paper in like one function call. Okay. My lecture slides are kind of like this. I have a single function that I'll show you in a minute that does everything for generating my lecture slides, so I don't have to do these things step by step. But I originally did them all step by step, and later when I realized I was doing them all step by step over and over again, I wrapped them into a function. Okay. So here's that bonus function I was talking about. This is the actual function in this class that generates the lecture slides, the PDFs of the slides, and the R code that you might use to follow along in the slides for this class. What this does is I've created a function called render and print my slides. It is a function which takes a number. The number is the lecture week we're in. Like for instance, I ran render and print slides 7 like 10 minutes before I taught today because I needed to update the slides. What this does is given, say, week 7, it browses to the directory where my week 7 lecture is in. It finds the RMD file for the particular week. It renders the R markdown document to the actual slides, the HTML slides, okay? It then generates some names to produce a PDF of the files and an R script of the R code in the slides. It makes sure the slides are rendered, giving it 5 extra seconds to write them to disk. It waits a minute, that's 5 seconds. Then it purls them, which extracts all the R code and generates an R script. So if you want to follow along in an R script instead of the slides, you can. Then it opens up a Chrome browser window in the background invisibly and prints the slides to a PDF and writes them to the directory. So if you're taking notes on PDFs of my slides, it's because I get Chrome to print them in the background whenever my slides are rendered. This is an example of a function I use constantly that actually saves me a lot of time, but all it is stuff I normally would have written like one line at a time in the past, but now I have this render and print function. I have another function that sits above this called generate class. I press it, it doesn't take any arguments. It takes this render and print slides and applies render and print slides to 1 through 10, thus knitting and doing the PDFs for all 10 lectures of my class in one button press. Okay. So practically, functions are kind of nice and I use them constantly, and it's so useful. So that's an example of a somewhat over-the-top function that none of you will probably ever need to use something like that. But I just want to show that, like, my day-to-day R stuff, I'm writing functions constantly, right? And you can do anything you want with them. Anything you've done many times, you keep typing over again, make a function do it. If it's repetitive, the computer should be doing it. Your time is valuable, right? Make the computer do stupid shit. Okay, so your homework. The homework is to some degree, the exact opposite of last week's homework. Last 2 weeks' homeworks was I gave you a hideous administrative data set with no explanation except what was in that R&D, and I made you bash your face against it until a result came out. What I'm giving you this week is a perfectly clean data set. This is it's data on the first year of Seattle's Pronto bike share program. It was if you were here and have been here as long as I have, right? So, you know, in eternity, there used to be these docked bikes that were all over the city. So there's a big dock and you had to lock a bike into it. You had to, like, I forget the exact mechanism for unlocking them, right? You pull them out, but you had to pick up the bike share bikes at these docks and take them back to the docks, okay? Some cities successfully use docked bike programs like this, but it didn't work in Seattle much the way the newer bike shares haven't worked and they're all going out because people don't like riding up and down hills and they don't like rain. Anyway, this bike share program failed. But they gave really cool data and they do data challenges with it. So this data set is actually taken from a real data science challenge that used to have like money prizes associated with it. It's a fun data set to work with. It is pristine. It's very clean data. Okay. What you're going to do in this template is you're going to write a loop, or I'll allow an lapply, or if you've been following, I just added, you could do a vroom call to do this, to read in the data from multiple files. So there's a few different files you're going to want to load in. You're going to write functions to clean up the data and use those functions. And then you're going to write a function to flexibly visualize the ridership over the first year, okay? So there's a little bit of string processing needed for this one, right? You've learned most of it, things like the substring and stuff, but you might need some other stuff that might come in the next lecture. I give suggestions in the template, but you might get the rest of it that you need in the string processing lecture next week. Okay, but I can cover it in detail in lab if we work together through these things. So the first half is due next week. The second half is due in 2 weeks. And those are the last required assignments for this class. The last homework after that is an optional homework for bonus points for people who care about bonus points in a credit, no credit class. Really, it's just for people who want to play with maps, right? But we'll get there. And yeah, Galen says in there, if they don't mind those things and they have their own bike, right? A lot of people in Seattle, if they ride bikes, they have their own bike. Bike share doesn't really capture those people. And those are the people who like riding up and down hills, by and large. I have a bike, and I still don't like riding up and down hills. Anyway, that's it. So if anybody has any questions, shoot. Yes, I am going to work through this homework step by step in lab. That is my solemn vow for the rest of the term, and like it's been before, is I will work through these homeworks in lab because I know that these homeworks can be tough and everyone likes to work sort of at their own pace. So your option is you come to lab, you work through it if you're not super comfortable doing it solo, but I usually have about half of the class or so goes through these things solo too, so you're free to keep doing that. Okay. You mentioned we could get R to utilize more than one core of our CPU. Is it possible to write a function R to engage multiple cores for other programs that don't typically use multiple cores? Yes, actually in an interesting way. So this is nothing unique to R. So what you could do, for instance, is you can use R to call system calls and run other programs. But what you could do is you could use R to run simultaneously multiple system calls. And if those system calls can be assigned to a CPU, you can essentially multiprocess things. But multiprocessing things is kind of introduces its own challenges. You need to have something there where you could have some sort of operation you want to run that can be divided up logically among multiple CPUs. Yeah, so, oh yeah, that's a common one. Drafting software often uses only one core. For things like drafting software and visualization type stuff, what I usually do is I pipe it off to my GPU. So there's multiprocessing like your CPU, which like mine might have like 8 cores or 16 cores. But my GPU has 1600 cores. And so for massively parallel operations, it's much better to farm it out to a GPU. And so you can do that kind of stuff through CUDA and stuff like that if you have an NVIDIA CPU. And actually statistical operations, you can actually farm out like Markov chain Monte Carlo to your GPU, and it's going to be faster than any desktop CPU too. So that's what I do for that kind of thing, but it depends. Multiprocessing is its own sort of, well, what's the word I'm looking for? It's a rabbit hole. Like it can be very difficult. Oh yeah, if you've got dual 1080 Ti's, then you could absolutely smoke stuff for rendering, right? Honestly, if you've got that kind of hardware sitting around there, I'd recommend you look into running R directly on your 1080s and having it do your processing for you, because that's going to be massively more processing power than any CPU, because R just doesn't efficiently use multi-cores. I mean, you could have like a 30-core Xeon or something, and those dual 1080s will smoke it. But it can be a pain in the ass to write it, and some things are slow on them too. But for visualization type stuff, yeah, that would probably be a lot faster. I'm not an expert in that. I just have a single old 1070, which is more than sufficient for running like data science-y type stuff. Dual 1080s would be monstrous. Yeah, I could send you links though. Anything else? Okie dokie. About a minute over. So nobody else got anything? I will see folks on Monday. I recommend taking a peek at the homework ahead of time. We will work through it on lab, and that's perfectly fine. And it'll be shockingly fast in lab probably too. It's a pretty short homework. Anyway, I'll see folks on Monday. Bye-bye.